In this video, we are going to look at corrosion thermodynamics, part 1, and we'll be able to cover corrosion cell requirement, free energy, types of electrochemical cell, standard electrode potentials, and corrosion tendencies, and Nernst equation. Why do we need to study thermodynamics of corrosion? The thermodynamics provides understanding of energy changes involved in electrochemical reactions. It also shows condition that may be adjusted to control corrosion, in which is in two ways. We have the immunity, which means that there is no corrosion going to happen on the engineering material, and we have the passivity, whereby an oxide layer is formed on the surface of the metal, which prevents or slows down the rate of corrosion. Let's move on to the corrosion cell requirement. So for corrosion to take place, we need to get all these things, right? So first, you know that current flow, that is the ions, right, in the electrolyte. This is electrolyte, and this is zinc and copper. In the electrolyte, the anions, which is a negative charge, move towards the anode, which is here, and the cation, which is the positive charge, move towards the cathode. So the positive charge move on to the cathode, and the negative charge move on to the anode. The salt bridge serves as what? Charge balance. So this is how it goes. And at the anodic side, oxidation is taking place because an electron is being released, which is zinc is equal to zinc 2 plus 2 electron, whereby the zinc is undergoing dissolution. And when you come here, the copper is being reduced to copper in solid, whereby copper 2 plus 2 e electron giving you copper in solids. So this is the cell requirement. Now let's look at the 4 prerequisites for corrosion. So for corrosion to happen, we need to have 4 things. The first thing we're going to talk about, we should have the anode. So we should have the anode, which is the anodic side. Also the anode of the metal surface, which is oxidation reaction. So oxidation reaction. So with the oxidation reaction, we can give example that Fe is giving you Fe 2 plus 2 electrons. And also we should have a cathode, which is a cathode, and a cathode undergo reduction reaction. And for reduction reaction, if I'm supposed to write reduction reaction for the cathode, we can get O2 plus 2H2O plus 4 electron, giving you 4OH minus. The third thing we need to get is an electrolyte. And the electrolyte in contact with the anode and the cathode, right? So it's the part for what? Ionic conduction. The final one for corrosion to happen is the electrical connection. And the electrical connection between the anode and the cathode, and it allows corrosion, or it allows electron to flow between the anode and the cathode. Now let's note this: if any of these, or if one of these 4 is missing, corrosion will not occur. So this is how. So for you to control corrosion, when you remove one of these, for example, you have a cathode, anode, and there's no electrolyte, corrosion will not occur. If you have all 3, one is missing, corrosion will not occur. Now, why do corrosion cell formed? Now, corrosion cell formed due to the difference in energy between the metal and the environment, right? So if there's different energy between the metal and the environment which is exposed to, then corrosion cell is formed. And variation could be 1, metallurgical. For metallurgical, we could talk about the composition of the material, the microstructure, the inclusion, heat treatment, welding, and fabrication. And we can also talk about the environmental factors, which can be the temperature-induced corrosion, which is caused by temperature, microbial-induced corrosion, which is caused by microorganisms, and environmental-induced corrosion, which is the stress corrosion cracking. Let's move on to the Gibbs free energy. So we talk about the change in energy, right? And this energy, the Gibbs free energy, help us to predict whether a reaction will occur or not, or the reaction will be in equilibrium. So let's take a reaction. Let's take this reaction. Given a reaction, A capital A plus B capital B is equal to small c capital C plus D capital D. Now, for this reaction, if the Gibbs free energy is equal to 0, then we can say that for this reaction, it will be in equilibrium. So if for this reaction, if the Gibbs free energy of this reaction is equal to 0, then we'll say that it's in what? Equilibrium. Now, let's look at something here too. If the Gibbs free energy is less than 0, we set it to be spontaneous. And for spontaneous, it means that the reaction will occur. So most of the time we are into this. For corrosion to happen or for a reaction to happen, the Gibbs free energy should be less than 0. Now, what if the Gibbs free energy is greater than 0? We term it to be non-spontaneous. And for non-spontaneous, it means that the reaction will not occur, but we can have some external current which will cause a non-spontaneous reaction to be a spontaneous reaction to occur. Are you getting? Let's take note of that. And let's look at G. What is G? Change in G is defined as a constant pressure and temperature. So this is defined as what? A constant pressure and temperature, and we call it the Gibbs free energy. Let's move on to the equilibrium constant, that is Kc. So for a given reaction, let's look at, we have the same A capital A plus B capital B is equal to small c capital C plus small d capital D. For forward reaction, right? For the rate of forward reaction, this is the rate of forward reaction. We could have that R1 is equal to K1 into bracket A exponent this, then times B exponent the B, small b. So we are looking at the reactant, right? K is the concentration of the reactant to their exponential. This is the number of moles to this one. So it's like we are using logarithmic rules to the exponent, and this is K1, which is a constant, which represents the equilibrium constant. So with this, we can also have the backward reaction. For the rate of backward reaction, we could have it to be R2. Let's limit to be R2 is equal to, this will be K2, then C small c, then times big D small d. And when you divide K1 divided by K2, this is called the equilibrium constant, which is what? Kc. When you divide this, we are going to have this A multiplied by B all over C multiplied by D exponent small d. And this is termed as the equilibrium constant, which is equal to Kc. Let's look at this graph here. We have the rate and the time. Now, the rate or the backward reaction increases with time. So the backward reaction increases with what? Time, and gets to equilibrium. So let's look at that. The rate of backward reaction increases with time, and the rate of forward reaction decreases with time, and join in to form this graph. So this is a forward reaction, which the rate reduces with time, and this is the backward reaction, which the rate increases with what? Time. So let's note that. Now let's find the relationship between the Gibbs free energy and the equilibrium constant, right? Yes. So now we know that, let's take a given reaction whereby we have A capital A plus B capital B giving you C capital C plus D capital D. So in that case, we know that we have that for you to find the Gibbs free of this, the total Gibbs free will be equal to the summation of the Gibbs free of the product, which in this case is the product, minus the summation of Gibbs free of the reactant. So this is the reactant of it. Then when you get to that, now we can know that we know that Gibbs free energy is equal to the G naught plus RT ln Kc, whereby the Kc is the equilibrium constant. Now this is at what? Isothermal. It's an isothermal reaction, right? Isothermal reaction. Then we know that at equilibrium, when you talk about at equilibrium, the Gibbs free energy will be equal to 0. At equilibrium, we know that the Gibbs free energy is 0. Then when you do substitution for the Gibbs free energy being to 0, we therefore know that here will be 0. So the change in J naught will be equal to negative RT ln Kc. And now we know that Kc has been established, and then you can put it inside. So this is the relationship between the Gibbs free energy and the equilibrium constant. Now let's look at the types of electrochemical cell, and this is Voitic cell or the galvanic cell. And for the galvanic cell, we have the anode, cathode. The electrons move from the anode to the cathode, and then this forms like the definition of galvanic corrosion, whereby we have the anodic and the cathodic reaction coming together, and the anodic member will undergo dissolution, and the cathodic member will undergo what? Deposition, based on the galvanic series, how close they are, and one being noble and one being the base metal. So then we have two types of the electrochemical cell. We have the Voitic cell or the galvanic cell, and we have the electrolytic cell. So this is an example of the galvanic cell, and it uses the principle of galvanic corrosion. So if you understand galvanic corrosion, we have two, the cathode and the anode, and then it's so with the Voitic cell, galvanic cell, it converts chemical energy to what? Electrical energy, so it can light up a bulb. So that's it. The Voitic cell or the galvanic cell converts chemical energy to what? Electrical energy. And for this, their reaction is spontaneous. So this one, for the Gibbs free energy is less than 0. Now let's look at the electrolytic cell. So this is an electrolytic cell. An electrolytic cell is an electrochemical cell that undergoes redox reaction when electrical current or electrical energy is applied. So we apply electrical energy. So this is an electrical energy which is applied for electrolytic cell. And what it does is that it converts the electrical energy to chemical energy. For the Voitic cell or the galvanic cell, it rather converts the chemical energy to what? Electrical energy. But with this, it's the vice versa, right? And the reaction is non-spontaneous, but it becomes spontaneous when there's introduction of this external voltage. So the external voltage drives the reaction for it to be what? Spontaneous. Now we have it. Electrolytic cell can be used to drive non-spontaneous redox reaction, which is also called electrolysis reaction. So we know that we have this in real life. I have the copper and the zinc, and then we introduce current. So the current or the external voltage will drive this, even though in a real sense it's not supposed to happen. We need to have some external voltage source which will drive the non-spontaneous reaction or the reaction to occur. I get it. So and the end is going to convert the this is the chemical the electrical energy to what? Chemical energy, and that's it. And with Voitic cell, as I said, the Voitic cell, it uses chemical energy and converts electrical energy, and this it converts electrical energy to what? The chemical energy. So now let's look at the table, the differences between the Voitic cell or the galvanic cell and the electrolytic cell. So the first one is, I said that the chemical energy to what? Electrical energy, and this converts electrical energy to what? Chemical energy. And the reaction for the Voitic cell or the galvanic cell is reversible or thermodynamic, and it is spontaneous. But whether the reaction is non-spontaneous, kinetic cell, and irreversible. Now here the cathodic member is positive, here the cathodic member is negative, and the anodic member is negative here the anodic member is what? Positive. And as we said that it's spontaneous, it will be less than 0, and if it's less than 0, each cell will be also greater than 0. From the formula, change in Gibbs free energy is equal to negative NFE. So negative NFE. So if this, for it to be this one, if this is positive, if E naught here is positive, right? If E naught is positive, then when you multiply by the negative, you get a negative answer, whereby the Gibbs free will be less than 0, right? But for this reaction, the Gibbs free is greater than 0. This is because the E naught is also less than 0. If it's less than 0, this will be negative. Negative times negative will give you a positive answer, which will make the Gibbs free energy being greater than 0. And then the reaction will occur. But we introduce some external voltage, which will make the non-spontaneous reaction to for reaction to occur. Example, we have the dry cell and the diurnal cell. And then we have electroplating, increase current, cathodic protection, right? Yeah. Now, let's look at the Gibbs free energy and the cell potential. So the free energy, that's the change in G, is related to the cell potential, which is E. By the formula, we have change in Gibbs free energy is equal to negative N Fe. And under this, we know that the N represents the number of electrons transferred. So this number of electrons transferred, we know that F is Faraday constant, which is 96500 coulomb per mole. And the E naught, which is the E, is the word cell potential. The E is the cell potential. Cell potential. And its unit is in volts. Let's note that. So, and the change in Gibbs free energy, the unit is what? Joules. Let's note that. So, the relationship between the cell potential and the Gibbs free energy is from this formula, that the Gibbs free energy, change in Gibbs free energy is equal to negative NFE, whereby the E represents the cell potential. Now, let's consider some reactions whereby I'm going to consider the zinc and hydrochloric acid cell and copper and hydrochloric acid cell. Now, for here, we need to write the anodic and the cathodic reaction. So with the anode reactions, we know that this is involving of hydrogen, right? So we have zinc, which is the metal, going under dissolution, zinc 2 plus what? 2 electrons, right? Yes. And the cathodic member, since it's in the presence of hydrochloric acid, and this is, let's assume it's deaerated hydrochloric acid, we are going to get that the reaction will be H, that's this cathode. You're going to get it to be 2H plus 2 electrons, giving you hydrogen gas, right? And they gave the potential, that's the cell potential of this, to be, that's E of A. E naught of A is equal to what? Negative 0.76 volts, 62 volts, right? 62. And the E naught of this is 0. The cathodic E naught is what? 0 volts. So for us to find the cell potential, that's overall cell potential, what to do now is that, note that this is based on, if they give it to you like this, and this is under dissolution, and this is it, and they gave you the EA to be 0.762 and the EC to be 0.0 volt. What to do now is that for us to find the overall cell potential, which is the E naught of cell potential, we are going to get that it will be EC minus what? EA, whereby we have our EC to be 0, so we're going to get minus 0.762 volts. So at the end, you're going to get what? A positive 0.762 volts. That is for this member. Now, this is based on the EMF series. The EMF series, and the EMF series, we'll get to it, but I want to brief it to you. It's all written in the what? The reduction form. And the more anodic member is, the more negative number. So when you see they give you two values and they don't even specify whether it is anodic or cathodic, what you must know is that the one which is more negative is the anodic member, and the one which is less negative is what? The cathodic member. From here, we know that the anodic member is EA because that's what? More negative as compared to the cathodic member. So you can do this. Now, note that for the EMF series, all is written in what? The reduction form. So if you want to, this formula, right, for the overall reaction, we can cancel it out, right? But ideal sense, if for the for this one given to you, which is 0.762 volts, in real sense, this should be in what? The reduction form, whereby you reverse the equation to be in the reduction form, right? For you to have the negative 0.62 volts. Are you getting it? Yes. And since we have a positive E naught series, that means that Will the reaction be spontaneous or non-spontaneous? Let's guess. So from here, we know that change in Gibbs free energy is equal to negative NFE, right? And in this case, this is positive. So I don't want to solve it. If it's positive, then what happened? It is what? Spontaneous. So that means that this reaction will occur. Spontaneous reaction. Okay. Let's look at the copper in deaerated hydrochloric cell. So in that case, we also write the anodic member, the anodic reaction, which we have Cu is equal to Cu2 plus what? 2 electron. And then we write the cathode, this one reaction, the cathodic reaction, we have the same thing, 2H plus 2E minus, giving you H2 plus. Now, they gave you the EA to be what? Positive 0.34 volts. And the EC, you know that it is 0. Now, for this reaction, when you are supposed to find it, now in this case, you are going to find that E cell is equal to EC minus EA. And the more negative number here, we know that 0 and this one, which is more negative, right? So therefore, we are going to get 0 minus what? 0.34. Are you getting it? And then 34 volts, and we are going to get negative 0.34 volts. And in that case, when you get E cell to be negative, what happened? It forms non-spontaneous. Now, in this case, we have two formulas for this. You can either use EC minus EA or EA plus EC. It's all based on how your reaction is being written. So in this case, as I said, the EMF series, right, is based on reduction. Like, it's always written in the reduction form. Are you getting it? So I can also use a different way to solve this. But it's appropriate that when you have EC minus EA, you don't change anything of them. Whatever they give it to you, just substitute the equation and use EC minus EA, and you are good to go to find the overall cell potential. So look at the same given reaction, replacing concentration by activity. So we want to know the relationship between concentration, which is C, and activity, right? So now let's go. When we use the same given reaction, which was given as A, capital A plus B, capital B, giving you small c, capital C plus small d, capital D. This is a reaction. Now we want to express this in what? In activity form. Then when you divide K1 divided by K2, which is the equilibrium constant, you're going to get activity of A, then C exponent C times activity of capital D exponent small d divided by the activity of. Move on to the derivation of the next equation. So we are going to prove the next equation. So let's consider the following reaction. We have A plus B reaction to give us the product to be C plus D. So in this case, let's know that the change in Gibbs free energy is equal to the change in Gibbs free energy naught, that is plus RT ln K. This is what we established, right? Now we know that our ln K becomes what? The change in Gibbs free energy is equal to change in Gibbs free, this one at standard, plus RT, then ln. Then you have the product, which is C times D, all over what? The reactant, which is A and B. And then we know that the Gibbs free energy can be also established that change in Gibbs free energy is equal to NFE. So therefore, we can also have, for the standard state, we're going to have change in Gibbs free energy is equal to negative F naught. So let's do some substitution into this. So when you do the substitution, you're going to get negative NFE is equal to negative NFE naught, then plus RT ln C times D all over A times D. And we can know that when you divide through by NF, you know that we're going to cancel it out. So when you divide by NF, there's a negative NF, negative NF. Divide through by negative NF. This is going to cancel this. This is going to cancel this. So at the end, you're going to get E is equal to E naught, then minus RT over NF ln, so ln C over D all over A times what? B. Then there's a relationship. So this is it. This is the formula for the next equation. We've proved it. Now this is the relationship between the next equation. That is the derivation. This is the next equation, right? This is the next equation. Now let's use this as standard conditions, whereby we have the temperature to be 25 degrees, which is 298 Kelvin, and we have our R, that's a gas constant, to be 8.314 joule mole per Kelvin. So in that case, we know that we are going to substitute that. And one thing I want to establish is that we are going to use with log, right? The relationship between the ln and the log is that ln x is equal to 2.303 log x. So therefore we can put inside. So when you do the substitution, at the end, we're going to get that our E is equal to E naught, then minus 0.059 divided by N log C D all over A B. So this is at standard condition. This is what we use at standard condition. So everything has been, we have that the Faraday constant, the F, you know Faraday constant is 96500 coulomb per what? Mole. So that one will be substituted into it, and at the end, this is what our standard condition. This is what we use. But if they give you non-standard conditions, then you go back to this formula, right? Yes. Let's look at the relationship between the change, the Gibbs free energy, the equilibrium constant, and the cell potential. We want to know what is the relationship. So we know from here, right? This is equal to negative NF E naught, right? This is negative NF E naught. The Gibbs free energy is equal to, from here, this is the formula we put here. So we know that G naught is equal to negative NF E naught, right? And then let's look at here what equation will relate this to that. We also established that negative RT ln Kc, that is G naught is equal to what? Negative RT ln Kc. And what about the E naught and the Kc? The E naught and the Kc, we established it to be what? RT over NF, right? Ln Kc. So we have that our E naught is equal to RT over NF ln Kc. So these are the relationship that you need to know. The three relationship. It's very important to know the relationship of this, right? It's very important. Now let's look at the condition. That is the relationship, right? The relationship between the same thing, but condition for spontaneous, equilibrium, and non-spontaneous reaction. So the condition, we have one. For spontaneous reaction, we know that the Gibbs free energy needs to be negative. And if the Gibbs free energy is negative, the Kc is what? Greater than 1. And the E cell, that's the cell potential, should also be what? Positive. I hope you understand that. And for equilibrium, know that the Gibbs free energy is 0, the Kc is 1, and the cell potential also will be 0. Now, with non-spontaneous, we establish that the Gibbs free energy should be positive. And when the Gibbs free energy is positive, the cell potential also become negative. And the Kc will be what? Less than 1. Let's take note of that. Now let's go. I talk about the EMF series, right? So I'm going to explain the EMF series. So from the EMF series, the top one, that is the more positive, or the top one represent the more cathodic, and the down at the series represent what? More anodic. But if two materials are joined together, you want to know which one will be the anode and the cathode. What I'll tell you that for the anodic reaction, it will be more negative. So let's compare. Let's use this. We have nickel and cadmium, right? The cadmium, nickel and cadmium. So for the, let's see which one will have which one will be the anode and which one will be the cathode. From here, which one is more negative, right? The more negative one is what? The cadmium. So the cadmium becomes what? The anodic member, and the nickel becomes what? The cathodic member. So if you want to find their E naught, you're going to get that the 0.250 minus 0.403, and you're going to get positive 0.153. We have this E cell, that the E cell is equal to what? EC minus EE. And since we know that the nickel is the cathodic member and the cadmium is the what? Anodic member, when you put it inside, you will be able to what? So, and in this case, when you put these two together, you know that the more anodic, the anodic member will undergo dissolution. So the cadmium will undergo dissolution. So cadmium will what? Corrode. Since cadmium is more anodic and it's more negative, right? Yes, it will corrode. Are you getting it? Yes, because the cadmium, the cell potential is less than the what? The nickel, as I said, right? That's solution concentration and temperature, the effect of that. So we have the standard and non-standard solution. For the standard solution, whereby I have 1 molar solution, you're going to have that. You're not going to solve anything because it's a standard. You're just going to find the E cell. That's the cell potential E cell, which in that case will give you the cathode, E cell of cathode over E cell of what? Anode. That's what you're going to get. This is it. And at the end, we know that the cadmium undergo dissolution, right? Yes. But at non-standard state, that's where you're going to use the Nernst equation. So this represents what? E. Are you getting it? Which is the E is equal to the E naught minus what? RT over NF ln X over Y. I hope you know that we proved that. Are you getting? So at standard state, is it at non-standard state, they have different concentration and temperature. But at standard state, it's same concentration, which is 1 molar solution, and temperature. Are you getting it? Yes. And for here, you apply, you know that the Gibbs free energy is equal to negative FE change in E naught. So this one will tell you that whether the reaction will happen or not, depending on the Gibbs free energy, because you are going to get this value. And if this value is positive, it means that it's spontaneous, and if it's negative, it's what? Non-spontaneous. Let's look at the summary of the standard EMF series. Metals with large positive potentials are called noble, right? Metals, because they do not dissolute easily, or did not dissolve because they do not dissolve easily. And these metals, we can say that they are cathodic metals. They are from the cathode side, right? And the potential of the noble metal is preceded by a positive sign. The electrode potential are thermodynamic quantities and have a little relevance to potential of metal in solution encountered in service. Yes. The EMF series lists only the electrode potential of metals and not alloys. These are some limitations. The series is based on pure metals, but more active metal such as sodium, magnesium, aluminum, zinc are called active metals. Alloys are not considered in the EMF series, but in the galvanic series, alloys are considered. From the reversible electrode potential in the standard EMF series of metal, it is possible to predict whether a particular metal will spontaneously dissolve, right? For prediction. Are you getting it? It gives an indication on how active the metal is, but does not necessarily predict the corrosion accurately. So to give that the corrosion will happen, but it doesn't predict the corrosion what? Accurately, right? Yeah. Let's look at some limitations. The limitation has been in what I read. So the EMF series lists only pure metals and alloys are not part. It predicts the tendency to corrode, but it cannot predict whether the corrosion will actually take place. And the EMF series can not always predict the effect of what? Environment. Now let's look at this example, and that is the last example that we'll be doing for this part. So what is the tendency of thin to corrode in de-aerated? The word is de-aerated. And when we talk about de-aerated, it means that there's no oxygen here in sulfuric acid. It has a pH of 2. Activity of tin is 10 to the power 6. The pH, the pressure of what? Hydrogen gas is 1 atmosphere at 25 degrees Celsius. They gave us the E naught for the reaction, which is for the tin, to be negative 0.138 volts. So for this, since it's not at standard condition, we need to use the Nernst equation. And before we need to use the Nernst equation, we need to find the E naught. That's the cell potential of it, right? Oh, the cell potential was given to us. And know that the cell potential for the hydrogen is 0. So let's write the cell reaction. So for the cell reaction, this is the cell reaction. We know that this tin is reacting with what? Sulfuric acid. And when it reacts, you are going to get what? Tin sulfate plus what? Hydrogen gas. So let's write the half reaction. So the anode reaction will be what? There's tin 2 plus 2E giving you tin. And in that case, our E naught is equal to negative 0.138 volts. The reason why the anodic reaction we did like this is that we are using the EMF series, and with the EMF series, it's all written in what? Reduction form, right? So for you to use this negative point, that's negative 0.138 volt, you need to write it in what? A reduction form for you to use it. You can also go, I'm using this method, it's a different method I'm using. There are two ways of doing this. You can also write it in the oxidized form, but you also change the unit to be positive, because the moment you write in the oxidized form, it means that you are changing the positive, you are changing to what? Positive, right? But this one, it has been reduced because the EMF series is based on reduction. It's the series, the value they gave it to you, they did all in what? In reduction form. They did all in reduction form. So to be on the safer side and for you to use this, it's better you write it in what? In what? A reduction form, and then you do it. So the cathodic reaction, since it's at D rated, we are going to have 2H plus 2 electron giving you H2 gas, which is a gas, right? So then this one, they gave us the EMF series to be what? 0 volt. All is written in what? Reduction. So what we need to do now is that we need to apply the Nernst equation. Please don't be confused of this, because the EMF series is written in what? A reduction form. So for you to use this E naught, you need to write it in reduction form for you to use it, right? Yes. So applying the next equation for here, the next equation I'm going to use that you're going to use, find the E, the standard cell potential of this, then the standard potential of this. So you find the E, capital E of this, and find the capital E of this, and then you can use your formula to know that EC minus EE, and you are good to go. So now let's go, because all is written in what? Reduction form. You use EC minus EE. So applying the next equation, you are going to get the E, you are going to do ox over what? Rad. So you are doing oxidation over what? Reduction. In this case, we are going to change the formula. You are not going to use negative. So in that case, you are going to get that E naught plus 0.059 divided by N, then log. You are going to use the, you see it is ox, so oxidation. So oxidation and over what? Reduction. Are you getting this? So this is going to be oxidation, and this will be what? Reduction. Because we are using positive here, we are not using negative. Please, let's take note of that. It's very important, right? When you are using this formula, it means that both equations are in what? Reduction form, because the EMF series is written in reduction form, and then you can use this formula. You can also decide to use the other one, which is the negative, and therefore you write this in what? The oxidation form, and write this in reduction form, and then you use that one formula to do it. So in this case, when we break it down, our E ox over rad will be equal to, I'm doing the for anode, the anodic reaction, you're going to get our E naught is what? Negative 0.138 volts plus 0.059 divided by the number of electron transferred is 2, then log. Our oxidation is what? SN2 plus, then over our reduction is SN, so SN. And let's note that the activity of a solid or liquid is 1, so here it becomes 1. So as activity of liquid and solid becomes 1, so here you change it to become what? 1. So at the end, when you are going to write, you're going to write E ox over rad is equal to negative 0.138 volt plus 0.059 divided by 2 log the activity of SN2 plus, right? And when you do the substitution, you put it in there, because they gave us the activity. If you go by, they gave us the activity of SN2 plus, this SN2 plus, sorry, to be 10 exponent negative 6. So when you do that, you're going to put 10 exponent negative 6 in here. So you're going to get negative 0.138 volt plus 0.059 divided by 2, then log the activity is 10 exponent negative 6. Are you getting it? And then at the end, you're going to get negative 0.315. Then this is for the anodic reaction. And then we'll do the same for the cathodic reaction. And for the cathodic reaction, we have E ox over rad is equal to what? the E naught plus 0.059 divided by what? N log. Now it's what? When you look at the reaction, you're going to get hydrogen ion, then 2 plus over the pressure of what? Hydrogen gas. And the pressure of hydrogen gas was given to us in the question as 0.8 atm. That is the pressure which was given to us. So in that case, here you're going to be 1, and log 1 is 0, right? So that place, when you expand this, we have this also to be 0 for hydrogen. So you're going to get 0 plus 0.059, and the number of electrons transferred was 2. Then log H plus exponent 2. Let's try expanding this, right? If we try expanding this, because they gave us a pH and we need to put a pH inside. So we are going to get that these two can come in front, right? Which is the law of logarithm. So we are going to get 0.059 over 2 times 2 log hydrogen ion. So this is going to cancel this. So at the end, you're going to get our E, ox over rad, equal to what? 0.059 log H plus. And you know the relationship between pH and log. You know pH is negative. pH is equal to what? Negative log of what? H plus, right? So when you do the substitution, that means that you're going to get negative 0.059 pH, because negative log of H plus is what? pH. So then we have our pH given to us, which was our pH was given to us as 0.59, and the pH was 2. So in that case, you're going to get negative, when you put that formula inside, you're going to get negative 0.118 volt. And this is for the EC cathode, which involved the hydrogen ion and hydrogen, and this is the EA, which is the 10. So for us to find the overall E cell, and to check whether the tendency will happen or not, we are going to get our EC minus what? Our EE. And our EC was what? Negative 0.118 minus our EA is what? 0.315 volts. This is always in volts. So at the end, we get our E cell to be positive 0.197 volt. And since we've gotten a positive value, that means that the tendency for thin corroding in deaerated sulfuric acid is true, because it gives us a spontaneous reaction. This is how it is done. Thank you very much for watching the thermodynamics of corrosion part 1.